Okay, the problem that I am going to speak of now is a bit lengthy problem. Okay, so you will have to keep your attention very tight on the board, otherwise you will lose track of it and repeating it will cost us a lot of time. So keep listening very carefully. So there are n doors, okay, and all doors are initially closed. Okay, there are n doors and all of those doors are initially closed. So just for sake of an example, I am taking n equals to 7. Okay, so initially all the doors are closed, so I am denoting them by closed 1, closed 2, closed 3, closed 4, closed 5, closed 6, closed 7. Okay, now there are n operations that are performed, n operations which are performed. So let me tell you, this will be your first operation, this will be your second, this will be your third, then fourth, then fifth, then sixth, then seventh. So n operations will be performed. So in the first operation, you toggle all the door numbers such that the number of that door is perfectly divisible by I. Okay, and your I is your ith step or ith iteration. So what I mean by that is, see, these doors are there and they are having unique numbers from 1 to 7, 1, 2, 3, 4, 5, 6, 7. Okay, this is how they are sequentially numbered. So in the first iteration, all those doors whose IDs are divisible by 1, you toggle their state. You understand what I mean by toggle? Toggle means that if it is closed, you make it open, and if it is open, you make it close. Yeah, you reverse the state. So what will happen? In the first state, I repeat, in the first operation, all the doors whose numbers are perfectly divisible by 1, okay, their states will be toggled. So can I say that after first step, all the doors will be open? So after first state, the doors will start looking like this: open 1, open 2, open 3, open 4, open 5, 6 and 7. In the second state, I will toggle state of all the doors whose IDs are perfectly divisible by 2. Okay, so can you tell me the state of which doors will be toggled? 2, 4 and 6, the state of 2, 4 and 6 will be toggled. So because just 2, 4 and 6 are perfectly divisible by 2. With 2, 2, 4 and 6 were divisible, so this will now become closed, this will now become closed, and this will now become closed. Everything will remain as it was, everything else will remain as they were. In the third state, what will happen? You will toggle state of all the doors whose IDs are perfectly divisible by 3. So what will happen? The state of this will, from open, this will become closed, and the state of this, from closed, this will become open, and everything else will remain as they were. Okay. Similarly, in the fourth state, what will happen? In the fourth step, all those which are perfectly divisible by 4, their states will be toggled. Can you tell me whose state will be toggled? Whose state? Just 4. Okay, because there is just one door whose ID is perfectly divisible by 4. So this fourth door which was closed will now become open, and everything will remain as they were initially. In fifth state, all those doors whose IDs are perfectly divisible by 5, just this one. So this will become closed, everything else as they were. In the sixth step, what will happen? For this one, it will become closed and everything else as they were. And in the last step, the state of this will change from open to closed, and everything else as they were. So in the end, how many doors are open? There are just 2 doors that are open. So the question is simple, that you are given this value n and you are aware that operations happen in this way. So your input is just n, which tells you the number of doors which are initially closed. All are initially closed. So you'll have to tell me when the operation ends, how many doors would have been opened. When all the operations are over, how many doors would have eventually been opened. So think, is there any approach So guys, let us try to take a look over here. So let us just try to understand that if there is a particular door, let's say door number 6. If I ask you a question that how many operations out of these n operations will touch this door number 6, can you tell me that? How many operations will touch door number 6 or have touched door number 6? Factors of 6, right? So 6 got touched in the first operation. Why? Because 1 was a divisor of 6. 6 got touched in second operation also. That is the reason this happened, right? Why? Because 2 was a factor of 6. 6 got touched in third operation also because 3 was a factor of 6. For 4, no. For 5, no. For 6, again, yes. So can I say that number of times a particular door is getting touched is simply equal to the number of factors of it? Number of times a door is getting touched is simply equal to the count of factors of it. Okay. Now, that is one thing which we have understood. Now, just park it somewhere. Okay. Another thing is, for a closed door to eventually become open, how many togglings should happen? Should the number of togglings be even or should the number of togglings be odd? Number of togglings should be, you're saying even, think again. Closed, open, closed. 2 togglings, right? Closed, open, closed, open, closed, 4 togglings. So only if number of togglings is odd, then the eventual state will be open. Is everyone clear with that? Everyone is clear with that? So what can I say? That all those doors, okay, whose numbers are such that the count of factors is odd, they would have remained open. Everything else would have remained closed. So for 1, number of factors is just 1, which is odd. For 4, number of factors is 1, 2 and 4, which is also odd. For all these, number of factors is even, and that is the reason they have remained closed. So what do I have to do? Before doing this question, we saw that a particular number will have odd number of factors only if that number is perfect square. So can I say that the answer should simply be equal to number of perfect squares in between 1 to n? Can I say that? The answer should simply be equal to the number of perfect squares in between 1 to n. Yeah, if you got it, now tell me what will be the number of perfect squares in between 1 to n? To count the number of perfect squares in between 1 to n, do you need to iterate from 1 to n or can you do that really easily? I think you can do that very easily because let's say the value of n is 100. Okay, let's say the value of n is 100. How many perfect squares are there in between 1 to 100? So can I say that there are just 10 perfect squares in between 1 to 100? And what are those 10 perfect squares? Those are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, right? So how did you come to this conclusion that there are just 10 perfect squares? By simply taking the square root of this number. So whatever is the square root of number, if the square root of the number is x, that means that the perfect squares that exist are 1 square, 2 square, so on till x square. So if you simply take the square root of your number, that should be your answer. That should be the count of perfect squares in between 1 to 100. So guys, what was the key concept behind solving this problem? Tell me. The key concept was that only for perfect square integers, the count of factors is odd. Okay.